Alright, another draft physics presentation. This one I'm going to put in the Daftloday section, even though it's on the subject of the fact that there's only one force, magnetism, and pretty much nothing else. Everything else is a manifestation of it, even gravity. And the force just has to do with electrons and protons and the fact of how they react differently polarized force. But it's all one force, two polarizations, two nuclear bits that are likewise polarized. Very simple. Anyway, and so that theory is being argued, and it's being argued in the context of electromagnetic theory as conventionally understood. So Daftloday is responding with now that something about special relativity has something to do with this. So I'll get to that in the second half of this video, just because that's a more complex argument, because it's all just mathematical gimmicks. We're back to Lorentz transformations and frame switching, as if that somehow proves magnetism and electricity are the same force, and apparently that same force is electricity, which is exactly the wrong answer. So amazingly stupid. So he has one link to a video by Jimmy or Toby, I don't know, some 15-year-old, doing relativity. That's the highest grade professional he could find doing the mathematics. And then a Wikipedia page that's complete incomprehensible gibberish, which is, clearly the mode operandi of modern physics is just to throw a bunch of numbers, do transformations, and pretend you accomplish something. When I think I can even demonstrate in this argument how their mathematics doesn't work in this case either. Just like their two-slit math isn't perfect, their math doing this crap, Maxwell's equations, breaks down because it really does have to do with this spatial argument. If you put even two magnets next to each other, they're no longer inverse square rule. As soon as you put the magnets a certain distance from each other, the inverse square rule breaks down. So their math isn't even accurate because it doesn't compensate for the breakdown of the inverse square law unless you exactly measure the sizes of the magnets. You're not going to get the right answer. So anyway, and so he says clear as mud in capital letters, and so he thinks this is like something constructive. Again, I have no interest in having some fucking verbal war with you, you dumb douche. My videos don't have any insults, merely as direct responses to yours. You said my hair is mop, I said your fucking head is bald, and I added you have a tiny, tiny, tiny fucking dick and little tiny balls, but you always have to resort to these garbage arguments. And you can't break this stupid, silly fucking habit of yours. You're a rude, obnoxious, by your own definition, retard. You can't learn to behave like a civilized ape. You're a dumb fucking mutt. Alright, anyway. I mean, he posts links to this clear as mud shit. I mean, this absolute shit arguments about how relativity has something to do with magnetism and electricity when it has nothing to do with it. And it's clear as fucking, it's not even mud, it's clear as asphalt, retard. Anyway, so then he says, you really haven't explained why a powerful neodymium magnet doesn't pick up lint or move a tin water stream, etc. Thin water stream. Oh, I did explain it. I clearly stated, I mean, I can redraw the pictures for you, I'll re-show you the same pictures. Magnets can't project their charge onto other surfaces. Unlike the 100,000 volt, what the hell is it called again? Veneer, I'm thinking. What the hell is this stupid thing called? Well, anyway, no matter how you put the voltage on, as I pointed out, static chargers are high voltage, low current. That means all the electrons are on the surface and they have a high potential, which means a high compression. They really don't want to be where they are, and they spring away from where they are very fast. Magnets have no such situation. They can't shoot electrons onto surfaces. So if you can create something that has 100,000 volts on it, I'll guarantee you the magnet will attract or repel it. So as soon as you can put the charge on the thing and put it in the area of the magnet, retaining that charge without that charge flying onto the surface of the magnet, I'm sure it'll be able to pick up things. It can't create charge in them. It can't project a charge. I made that clear. The magnet is made of solid material. The atoms are rigid. The electrons are not mobile. The magnetism is being created by the inside of the magnet, not a surface charge. I explained that quite clearly. So anyway, so we'll get to now the explanation of water. Now, I don't want to get into this much detail, but again, he's going to force the issue. So instead of acknowledging that, yes, it could be possible that this is what happens, blah, 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 instead he just makes this, obnoxious argument as if he needs more information. He has to have every detail explained to him personally. And it is, some of the physics is a little bit complicated. But this idea that water is ionized easily, and that moving charges, once you have an ion, when you move an ion, it doesn't have to be moving through a conductor. It's a moving charge. And once that charge starts moving, it creates magnetism in any paramagnetic or ferromagnetic material in proximity to it. And vice versa. That it causes a chain reaction, that any charge moving in that field is not only going to be moved, but it's going to create more charge. Alright, so there's this thing Professor Lewin did with tin cans and water, and it created a high voltage. I would call it a kind of capacitor myself, but it's a battery essentially, and it's a high voltage battery. You were talking 10 to 20,000 volts of static charge that the water collects just by falling through a simple device. And so I will let him say it one way, and then I will explain another way. He does a detailed explanation in another video, but I'm not going to do the detailed explanation because, first off, I don't think it's entirely correct. Alright, so yeah, so I guess we'll just play this video and then I'll do some drawing. Alright, so this is the diagram of it. You can see the diagram. Okay, 2 tin cans with the bottoms and tops cut out, and then 2 cans at the bottom, insulated. They're on insulated surfaces, so ground can't get to them. And you connect the left jug to the right can, and you connect the left can to the right jug, right? Well, you get it. It crosses over. So the water that travels through the round cylinder on the left side ends up sending its whatever charge it has to container C, and container D, as he has them labeled, gets the charge from the can B. If you can see that. And the key to the thing is the fact that, well, I'll let him say it.
And this water also runs into a conducting trash can. And now comes a key point. That this conductor here, A, is connected through a conducting wire with C, and the conductor B, the paint can, is connected with a conducting wire to this trash can D. You let the water run for a while, and you will see between these 2 points here sparks. Even when the points are as far apart as, say, 5 millimeters, when you're talking about at least a potential difference of something like 15,000 volts, you will see the sparks. And you wait, see another spark. And you wait, and you see another spark. So this is a power supply. And there must be energy coming from somewhere. And so problem 4.1, which you haven't seen yet on your fourth assignment, is asking you how this works. I will demonstrate it today, and I will come back to it later. The way it works is actually quite subtle, but I want you to think about it. It's a remarkable battery, a remarkable power supply.
Yeah, and I would argue it's even more remarkable when you actually understand correctly how it works. But regardless, it's really, really is. When I first saw it, I was like, that's pretty amazing.
As the water starts running, I want to draw your attention to the fact that you can almost anticipate when the spark occurs. Because the water at the very last is beginning to spread. It doesn't come out anymore just like a narrow cylinder, but it begins to spread. And then comes the spark.
Right, because the can has charged a very high charge. 15,000 volts worth of charge is now on the can. So the water spreads because the ions that are being created by the dripping faucet, the faucet's actually the first thing charged, and that charge ends up dictating the whole function. So there's positive ions coming out of one of the streams and negative ions coming out of the other stream.
And then it goes back to running normally, and then slowly in time it will spread, and then comes the spark.
Now, see, if you don't let it spark, it'll stay spread. So you might be able to build up. I don't know how many volts you might be able to build up. So you can, he could put the little gap further apart and allow it to continue to build up charge, and it might build up 50,000 volts. I don't know what its maximum breakdown voltage is. I don't know. But I think if you, especially where the wires cross over, if you insulate the wires very well, keep them far enough apart, you might be able to get to 100,000 volts. But it's going to be a little more complicated than just, you can't just run the wires within 6 inches of each other, because then you'll still have a breakdown voltage.
Here, Marcos and Bill spend a lot of time getting this going. Marcos, do I have all my lights the way you want them? You're happy with that. There you see the two balls, which are really here.
So those are just the two.
Look at this.
Those are just the two wires coming off the two bottom buckets. So that's the charge on the bottom buckets.
Sparks. So I will start the water running now. Let's just be patient a little bit. And let's see where we see in spark. Did you see one? Did you see the spark? Oh, you were not looking.
No,
man,
I didn't see
paying
it.
for this. Look at the two balls. Give it some time again. Have to charge up. I can already anticipate it's coming up. It's coming up. Yeah. Did you see it?
No.
15,000 volts.
But
let's give it a little bit more time, and then we'll
let's
take
assume
a look at the water flow.
They actually get it right.
I can see from close. But we can make you see the water flow. Look again. It's coming up. Did you see it? I could see it coming up. I can make you listen.
They keep
by
missing
having my microphone near the water. You can hear this water running. Familiar sound to all of us. And now the sound changes. You hear change, and there's a spark.
There you go, finally. All right, so yeah, so I guess I'll draw it and do it that way. I guess I could have taken this image maybe and drawn over it, or something like that, but I don't think we need to do that. So it's just two tin can, straight through, and then two buckets, all metal, and they're color coordinated based on how they're connected with these little wires you see here. Like I said, if they separated these wires, made sure they weren't very close to each other, they could probably build up a significantly higher charge. Probably, I would guess. Alright, so we will switch to drawing mode. Hopefully. Mostly. Alright, so Daftloday's demand for an explanation of how water charges. So here's the two outlets, here's the two cans. I might as well color coordinate them also. And the key is this goes black also. So this is the red bucket, and this is the black bucket. So these are connected, and this is connected. Alright. So the idea is what's happening is one of these systems, it could go either way, technically. I mean, if you made this experiment perfectly, everything was insulated the same, and there was no walls closer to one side than the other, it might randomly, so to speak, from your perception, you wouldn't be able to predict what side goes positive, what side goes negative. But I would argue there's probably a fault in the ground in one of these. One of these is probably is closer to a ground than the other, and one of them, therefore, will decide to go negative. But anyways, let's just say for the sake of this argument, this one's the negative, and this one's gone positive. In the sense that they will, I don't even know how to put that. But anyway, it's going to go through the actual water that's being fed, is actually going to be affected by this charge difference. So this charge, whatever this nozzle goes, it creeps up the water a little bit. And so once one of them goes, the other one goes the opposite. Alright, so once you've established that, what's happening now then is the water is ionized to some extent. And when that happens, the more the bucket gets charged, that is, the more water that gets in it, the higher the charge goes. Okay, so if you don't allow this gap. So if you don't allow the spark gap to kill the experiment, they would maintain their charges. So the idea is so the water starts off going pretty straight, but as the charge starts to build up from these little ions moving through this field, the ions are essentially a moving charge. They create a magnetism in the can, eddy currents. The eddy currents shoot back a magnetic field, and that's why the ions move to the surface of the can, is because they're oppositely charged, so to speak, than the ions that end up in the bucket. So these ions, let's say they're all negatively charged, they end up going inside of this positively charged bucket, so to speak. I don't know how to say this right. The can is negatively charged, this can is positively charged, I guess is some way to say it. Well, anyway, it's the opposite charge idea. And so obviously the water starts to spread because the ions are attracted to the surface of the can magnetically. And so that's essentially the argument I was making before. Okay, the part that Daftloday considers clear as mud, I suspect, is the fact that when you have two charges that are on surfaces, what the electrons especially are going to do is pile up where they sense a weakness in this, any strength in this field. So any little place where there's a little bump, or anything's closer, where this field is a tiny bit closer, this high proton, sorry I read that in black, but anyway, the electrons are going to start piling up. And as they pile up, that means the protons are going to move away the more the electrons pile up. So it's going to increase the strength of the electrons, but there's going to be even fewer protons around. The same thing is going to happen on this side. So where these electrons pile up, these electrons that are still on this surface scatter, they go away. So they all head away. So the electrons are all moving away. So this is becoming more positive. And the two more positiveness, because the electrons are running away, this gets more positive. As this gets more positive, this gets more negative, which means more electrons pile up. And the two induce, essentially, the field being moved to this lump. This is where the strength of the field is now. So the static charge that was on one object is no longer. So if I have an object like a piece of confetti and I have the Venn diagram, what's really going to happen is whichever one has the electrons, the excess of electrons, those electrons are going to move towards the Van de Graaff. And so what was a charge all the way around the piece of confetti is essentially going to change into a charge moving towards the Van de Graaff. So the magnetic field that was created is now going to be a lot different than an inverse square kind of field. It's going to be a really, especially at this point, there's not going to be an inverse square rule anymore. It's going to be a very strong connection between the proton on the Van de Graaff and the electron on the confetti. The electron on the confetti is essentially going to be moved all the way out here by the fact that all these atoms in this field are going to become charged the same way as the confetti. The confetti is just going to work its way, in terms of the charge on the confetti, is going to work its way to the Van de Graaff, and in that sense pull the confetti towards the Van de Graaff through that action. And obviously if you could move the confetti quickly towards the Van de Graaff, you'd get a spark, you know, if it needed to do it that way. You probably get one anyway when it moves towards it, you just don't see it. So you can see this in like if I had one of those Tesla ball things, you could it's the same effect, right? Because you're basically creating a plasma, you know, a bunch of electrons in a vacuum, I would imagine, of some kind, so in the ball, and you have this high voltage, you know, I don't know, 50,000, 100,000 volts, I don't know what it is. But anyway, and what's happening is you can see, because of the blue light that comes off the St. Elmo's fire, they have some other word for it, but you can actually see the effect I'm talking about, in the sense that the anode is producing a bunch of ions. It's actually breaking down the anode. The anode is breaking up into little atoms that are flying off. So they must degrade over time, because little molecules are flying off of it, and those molecules are doing exactly what the electrons in the Van de Graaff are going to do. They're going to start moving to where they sense a ground, you know, any oppositely charged thing on the surface. So if you place your fingers on the surface, that's where the charge will go, because it's sensing that ground. It's feeling it, in the sense that it's feeling the low potential, the low pressure, the absence of force, the absence of repulsive force. And it's the absence of repulsion force, that is the absence of electrons. So wherever you don't have an electron, okay, if I have electrons here and electrons here, and I have a place where there's an absence of electrons, relatively speaking, that's going to be the obvious path that the plasma will take, and you get to see it because it glows with photons as the ions are reionized, as the bits of chemistry are converted into ions, and then they do the reverse. They turn back into neutral particles and fall as dust probably somewhere inside of that globe, or stick to the sides. I mean, over time the thing probably discolors or something else. So I mean, it's not a last forever kind of device. Alright, so the key point is, first off, the inverse square law in any one of the Maxwell equations or anything else, it doesn't really mean anything unless you do take into account how big your surfaces are and how they interact with each other. Because in all of these sections, so to speak, all the energy or potential in these sections wouldn't be obeying the inverse square law. The only ones that would be obeying it are the ones here on the ends. But everything else is not going to be obeying inverse square rules anymore. It's going to be a much stronger force. And so that's a key point. The second point that's a key point is electrons move. They're free electrons, and they will seek, they will be pulled. And when they are pulled, they essentially take with them the magnetic field they create. every electron is a magnetic monopole. So the more electrons I pile up, the more of a magnetic potential I create. The stronger the magnetism of any thing that is that has mobile electrons. So again, the only difference between a magnet is that the confetti, when you're dropping it near a Venn digraph or near a comb that's been charged with 50,000 volts, when you drop a piece of confetti near, you pick it up with that comb, what's happening is exactly as I stated. Electrons are all flying off of this thing. So if you did it in a vacuum, it's not going to pick up it's not going to be able to pick up the confetti, because it needs some atmosphere. I'm fairly certain. Maybe it doesn't. Well, electrons just don't travel through nothing. I mean, they need an atmosphere to travel through, usually, because they can't make the long trip. An electron can't go a long distance on its own. It needs to hit an atom, and then another atom, and another. It needs to make ions, and the ions jump the electron. That kind of thing has to take place. But anyway, the real point I want to make is magnets don't have free electrons. Therefore, they're not shooting electrons into the atmosphere between the two things, and therefore they can't charge the confetti. They can't put a charge on the surface of the confetti. But if you charge the confetti will move in a magnetic field just like a compass needle. It will move. But you have to charge it. So that's why magnets don't pick up confetti, is because they're not shooting electrons. They're not creating a charge on the confetti. And they're not doing the second half of the bulging argument. So the problem is that say if you had the negative charge on the confetti, well, if you had the negative charge on the confetti, you're going to be able to pick it up, so that's not going to work. There's just no way to charge the confetti with a magnet. So you have to charge the confetti before the magnet can affect it. It's just the way it is. It can't pick up uncharged confetti, and the Venn digraph charges the confetti. Something with the comb charges the confetti. As you bring the comb near, the 1,000 volts is reaching out, and it's landing, it's hitting the confetti surface, and it's putting charge on it. And then the confetti can flip even, Alright, so I did explain that. So it's just bogus to say I didn't. Another little bit another thing just occurred to me when I was talking about the atoms is one of the interesting things. So, I guess I'm going to have to get into chemistry eventually, because you people are just insufferable jackasses. Excuse it, but that's what you are. You're rude, insufferable jackasses. So anyway, the ions of hydrogen, let's call them, it's basically you have a neutron, okay, which is a pair, a proton and an electron, and then you can have another version of hydrogen, that is an electron with 2 protons. And I guess you can have the third version, which is a proton, a neutron, and an electron. So if you always understand that neutrons are essentially just a pair of protons and electrons, a proton and electron. If you understand that that's what a neutron is, then a neutron is this package, then when you model these atoms, it gets a lot easier to understand what the configuration is. So my argument is when what hydrogen is doing is the 2 electrons are opposite the single proton in the neutron, which means the electrons are very close to the neutron, the proton that is the neutron. Alright, and the interesting truth is that creates a weird field out here, because the close distance of these electrons means that any electron that tries to get close to the hydrogen atom can't really do it, because this repulsive force is much stronger. See, if the repulsive force had to come all the way from over here, it would be fairly weak. See, the longer the line, the weaker the force here in this example. So these short lines mean strong force, long lines mean weak force. So an electron, if if the electrons were at their normal distance, in the sense that they didn't have this outlet that was letting all the black reflective force out, and they had to stay their usual distance from each other, they couldn't get this close, then there wouldn't be such a repulsive pressure to anything trying to get to this proton. So essentially that's the nature of the hydrogen atom, and I'll go to the helium, and then I'll go to explaining a water molecule and why it is charged, why it easily creates positive and negative ions in somewhat equal proportions. Anyway, so that's another conversation. So let's just do the relativity thing and be done with this. I don't think we need any more drawings for that. I don't think I'll bother with drawings. I mean, it's all mathematics, and I'll just attempt to explain why the mathematics is pretty much rubbish. Let's see. The electric field understood. No, that was a different video. And that's subscriptions and uniform using special relativity. So this is it. Alright, so let me just play the last bit of this, and I'll try to explain what this kid from MIT is saying. But this is the video Daftloday provides. Okay, not exactly. First off, the kid doesn't speak very well. You know, I mean, it's somewhat messy English, some kind of accent, which makes it a little difficult. Alright, so I guess I do need a drawing. Yeah, we'll do the drawing first, just because it's kind of critical to understanding the gimmick. You know, it's just a gimmick. There's nothing more to it. But you can see in the image here that it's, you know, he's got what's basically a conductor, and then he puts a test charge. So I think it started off with two plates, and they're saying one is length contracted and one isn't, or some kind of, I don't even think you need to go through all that nonsense to understand the gimmick. So I'll draw it a different way that I think is fairly represents the substance of this argument, which is just garbage. So you have, let's say you have three elements. You have the wire, you have the electrons in the wire, and then you have a test charge electron, let's say. And so he basically says, okay, well, this is the standard way of doing the equation, is you assume that this electron is doing the moving, okay, that there's a volume of them moving through the wire, and that's going to create a charge density, and this thing's going to be affected by, through Maxwell's equations, the amount of charge created over this distance. And again, the distance thing breaks down because under certain distances, these two electrons are essentially going to start communicating with each other directly. There's not going to be any inverse square law. There's going to be a beam of communication between the two, and it's not going to have anything to do with inverse square law rules anymore. But anyway, so what they're doing with this relativity argument is they're basically forgetting about that reality, and so just redrawing it again, they're going to say, let's pretend that we don't know how this thing works, in the sense that we know relative, like in the real experiment, we know which things are moving. We know the wire isn't moving. We know this charge isn't moving, and we know the only thing moving are the electrons inside. But they're basically just saying, well, let's pretend we don't know that. Alright, and let's play some silly relativity game, where now we're going to say this charge is moving this way, this charge isn't moving at all, and but it's essentially what they're really saying is this charge isn't moving, this charge isn't moving, and this wire is moving. So those are the three ways you could look at it. This charge is moving with a density of charge. The whole wire with its density is moving and the charge is standing still. Or you can move this charge and leave those things not moving, if you get what I mean. Alright, so that's the game they're playing. And somehow by playing this silly game where we pretend we don't know which one we're measuring, they say that they get an equation that equals the same thing. And it basically writes something as silly as E equals E plus squiggly bullshit. And they say, like, this is rational mathematics. E equals E plus squiggly bullshit. Which can't possibly be true because we know that squiggly bullshit is some real number. It's not. Squiggly bullshit is not 0. So how the fuck can E equal E? And you say, oh yeah, that's a rational equation, when you know squiggly bullshit isn't 0. I mean, it just makes the whole thing silly. But it's just a mathematical gimmick. And so Daftloday thinks there's some, because they use a Lorentz transformation. Again, let's understand what they're basically doing too is just breaking down. They're forgetting about the inverse square law, the distance, all right, and converting that instead into a Lorentz transformation to take the place of the inverse square law. I mean, not exactly, brilliant. I mean, they're basically just turning the rule of the inverse square law, the fact that the lines diverge at a specific 4 times with half the distance, they're just taking that rule and converting it into one of these stupid Lorentz curves and then applying that curve as the reality when we already know what the reality is. You don't need to draw it. You don't need to turn it into a curve. But that's all that's really there. Alright, so we'll play the end of it. So it's the whole video is just a ton of mathematical diversions. Is that what they're called? Oh, derivatives. Yeah, a bunch of transformations and derivations. So a bunch of just conversions and perversions of mathematics to get shit to equal shit. But it's just shit equaling shit. Alright, so play some of this shit.
This force is going to be, the prime force is going to be the same as the original force times a factor of gamma.
Yeah, so F equals F except plus this. I mean, it's just stupid on its face.
Now, this makes completely sense with our the special relativity we covered in the beginning, but we have to think about what's going on here. This force, which we first saw on the lab frame when we assumed that this was a neutral wire, was produced by a magnetic field. This force here...
Right, so a neutral wire, which doesn't make any sense, right? The neutral wire can't create any force, and one single test particle can't, by moving, create enough charge. So they're just reversing the magnetic field and the electric field, and saying because we can reverse one, I mean, we can make one look strong and one look weak, doing the equation one way, and then we can just flip it over and do the equation the exact opposite, upside down way, and one is strong as one is weak. That proportion already exists. You don't need a Lorentz transformation to know that's always symmetrical. The weakness of one field and the strength of the other field is always symmetrical. They're always proportional. So, I mean, it's not some brilliant revelation of special relativity that we understand the relationship between those two things are proportional. And again, the two things, one of them isn't a real thing. There is no electric field.
However, is produced by an electric field. The forces are equal. The only difference of the gamma has to do with the transformation. But let's think of, so the magnitude is not the word.
The magnitude is not important. So again, they're doing equations where, no, the magnitude of the equation isn't important. I think it's important.
What should worry us is, why are these forces so similar? We used to have a magnetic force, and we used to have an electric force.
because it doesn't really matter. Yes, if I move this pen across this surface, or I move this surface across this pen, they're going to be the same thing, except this isn't going to be able to create the same energy as this moving, because they're not the same energy. So again, if you're saying you have one charge moving through the wire and then one charge to test that one charge, as a practical matter, you can't do that experiment because you ain't going to get shit. So unless you have those two charges really close to each other, your equation is going to come up with a number like 0.0005 times 10 to the minus 12. It's not going to come up with any kind of real force here, because you're just measuring one charge passing another charge, and you're forgetting that the wire even exists, which is bullshit.
Well, that's what explains that the electric force and the magnetic force is the same thing.
I mean, understand, when one charge moves across the wire, so let's say this is one charge, because we'll just use the tip, and this is the wire. The wire has a whole bunch of electrons in it, so if I moved one charge across it, it's obviously going to have a relationship with each one of the elements of charge inside the wire. But clearly, this one charge would have to move much, much slower. What? No, it can't. Even that won't do it. It can't do the volume of interactions that can take place if you move the charges in the wire. So if you move the million things, you get a lot more movement than if you move the one thing.
An electric force and the magnetic force are the same phenomena occurring at a different frame, at a different perception.
Yeah, so again, this idea that somehow you change the reality of the circumstance, somehow there's a mechanics here that's frame-based. It's just bullshit. Electrons move a certain way, protons move a certain. There's certain rigid rules that they follow, and it's just nonsense to say I can frame myself into any scenario, because there are forward and backward rules.
This particle, we'll see that the particle itself is not moving, so it can therefore not experience a magnetic field, because you need a velocity for that.
They can't create one. Yes, if nothing's moving, there won't be any magnetic or electric field. True. But if anything's moving in the experiment, it's going to experience that thing getting closer to it, and it's going to be likely that it's getting closer because it's moving towards it. That's going to be the truth. So again, this fucking nonsense math doesn't give a fuck about reality. It just gives a fuck about making some sort of mathematical equation that balances out. And again, it doesn't balance out because these assholes aren't even obeying the rules of the inverse square law, which is, it's not a fucking law. And it doesn't work when things get close to each other.
However, if I see the particle moving and I see this wire stationary, I will think that whatever second of this particle must be a magnetic field. The particle will feel, no, you're wrong, it's going to be an E field. And I'm going to be like, no, you're wrong, it's a magnetic field. And
so again, they're just reversing the intensity of the fields by changing this frame. So it has absolutely nothing to do with the fact that the electric field is much weaker. And again, it's not a field. I don't even know how to... The movement of the electrons is changing the proximity of the magnetism. But that's all it's doing. It doesn't exist as its own field. The stuff I drew is dimples, where the charge is migrating into the field. That's an electrical phenomenon, and it migrates the magnetic field closer to the object, intensifying the magnetic charge, the magnetic influence. The magnets are now closer, that means the force between them is stronger. So you think the charge is here, but the charge isn't really here, because we're talking about bigger charges, right? We're not talking about fucking single electrons. And again, if we were talking about single electrons, their math still wouldn't work, because they still don't understand that single electrons are not communicating based on the inverse square law. But anyway, if you took the charged element and we have the other wire, the point is the charged element looks like it's staying here, but it's not staying there. just like the plasma, it's moving the magnetic field into the space. And that's why the magnetic field gets so strong. Is because the electric field, which isn't a field, it's a circumstance of the movement of the electrons. The moving electrons migrated the magnetic field closer to the other object. So anyway, so this has nothing to do with special relativity. This is just such a pile of shit. The only relationship between special relativity and electricity and magnetism is the one Maxwell created, because it's fucking Maxwell's equations that Einstein merely transformed into gravity equations. That's the only connection.
And that's the beautiful thing about relativity, that nobody's wrong.
Yeah, nobody's wrong. I mean, just, yeah, we can just make it up, man. It's, who cares? 3 bears, 3 pigs, 3 blind mice. It just doesn't matter. We'll tell any fairy tale.
What happened is that it is experiencing what we think is different, but it's actually the same.
It's experiencing something different. It's obviously different in the equation, and the fact that E does not equal E plus Q or whatever squiggly line you want to make. That can't be right. It can't equal E plus something that's not 0. That can't be true.
Of course, and it's the same phenomenon. And this is the beautiful connection of how special relativity connects the same effects of electric field and the magnetic field. As you can see by this result, they're the same thing. They just have the factor of gamma.
Just have the factor of the completely different thing that, yes, the two have a proportion. Maxwell reestablished their proportionality. You don't need special relativity to know there's a proportionality between the electric field and the magnetic field. So it's just all rubbish. Just get to the end of this piece of shit.
Which is necessary for any force transformation. And this just shows an example of how these two relate really well and really beautifully. Just giving another last note on unification of forces. This unification of electromagnetism and of electric force and magnetic force occurred in the...
Again, it's no unification. This is just bullshit. They've explained nothing. They've dealt with not a single cause or a single mechanical function. Obscene.
19th century and all that. And in this century, the last century, 20th century, we actually discovered, we humans, that the electromagnetic force is the same thing as another force we call the weak force. And we can assume that at some...
Yeah, well, eventually you're going to figure out that the electrons and protons are magnetic monopoles, and that's what's explaining the strong and weak force. But I mean, the weak force doesn't even have a definition anyway, so bullshit on that. All right, this is the Wikipedia page. What's on this classical electromagnetism and special relativity, and it's just gibberish, blah 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 blah. Insanely stupid diagrams that don't explain a damn thing. Like Billy sees spot this way, Sally sees some other kind of bullshit because Sally doesn't have she's not moving, but Billy is moving, and then vice versa, and somehow that says it all. So a bunch of mathematical gibberish with silly symbols and fucktard, crap, bullshit. Here's the sentence I found interesting. Alright, let's see. The above transformation rules show that the electric field is in one form contributes to the magnetic field, in another frame vice versa. So in one field, they said, let's see, the magnetic, see, they're not even written well. The above transformation rules show that the electric field in one frame contributes to the magnetic field in another frame, and vice versa. This is often described by saying that the electric field and magnetic field are two interrelated aspects of a single object, called the electromagnetic field. Please. Indeed, the entire electromagnetic field can be encoded in a single rank 2 tensor called the electromagnetic tensor. See below. No, I don't think I'll do that. All right, let's see if I can tell. There's more a statement I find even, it's more important here. One part of the force between moving charges we call magnetic force is really one aspect of an electrical effect. So there you go. This is a quote from Richard Feynman. One part of the force between moving charges we call magnetic force. It is really one aspect of an electrical effect. So it's exactly backwards. The electrical force is just a manipulation of the magnetic field. The electrical force is just electrons moving or migrating, which is the same as charge moving. And when the charge moves to another location, it creates a different magnetic relationship to other charges, period. And magnets can't migrate charge. All they do is produce the force of magnetism. They don't impose electrical how do you put it? They can't migrate the actual elements of charge. Now, clearly magnets can induce magnetism in other metals, paramagnetic materials, by being moved across them and then creating electricity, okay, which is just electrons moving, and where they're moving, they're changing the magnetic character by changing the domains. So the domains change, the object becomes magnetic, but the magnetism was already first created by moving the electrons in the metal. The electrons are moved by the magnetic force. There's no electric force that moves stuff. It's the magnetic force, if you want to be honest to it. I've called it the proton and electron force, but I mean, obviously the proton and electron force become magnets when you polarize them. There's no other way. It has to be called magnetism first. The fact that it's one force is the argument being made. And clearly they're not making that argument, in the sense that they're not accounting for the force being the cause of the movement of electrons. The force that moves electrons is magnetism. Alright. That's enough. So, yeah, I'm going to respond to rudeness with rudeness. So if you can't clean up your acts, then yeah, you're going to get what you deserve. I mean, this isn't that complicated. I don't type this kind of rubbish on other people's videos. I just don't understand why you think you have a right to type shit on people's videos and then they're supposed to say thank you for that shit. I mean, if you can't make a civil counter argument, and I didn't make an uncivil argument. There was nothing in my initial video where I said Daftloday is an ugly, dumb, smelly sack of fat shit. I didn't do any of that. So he has no right to soil my comment section with crap. Rude crap. Alright, so till the next time. Look, you're not going to win this argument, Daftloday, because this one's really high on my confidence level, so I can do these all day long. Because I've been through it already. I've watched all the lectures. I've seen all the phenomenon of magnetism and electricity. And this theory clearly fits. So, fuck you. Really. Just go ahead. Go ahead. Try to come up with some other experiment. I'll give you an explanation for it. Yeah. Except I'm not doing any of those black box ones. Your magic special entanglement experiments. Fuck that shit. Your, we can see photons experiments. Anyway, enough said. Till next time and such.